Welcome to this video. The topic will be the proof that the Lebesgue measure is an outer measure. Before that, we will first establish the definition of the Lebesgue outer measure and show an example of how to apply it. So we need to define first a Borel measure. So we have a Borel measure lambda that is defined on a Borel sigma algebra B in an n-dimensional real number space. All right, and the measure lambda is then defined like this. The starting point was that we have seen that the measures on Borel sets are incomplete. That means that they cannot measure every negligible set. We saw this problem appear with the so-called Cantor set. And one way to define a complete measure is the Lebesgue measure. So we want to define a measure for any volume E that's a subset of capital omega. So E doesn't necessarily have to be an element of the Borel sigma algebra, all right? But capital I, those volumes here, are part of the Borel sigma algebra and are therefore Borel measurable. We can find now a union of those capital I that cover up E. That's what's written here. So E will be a subset of the union of those capital I that are Borel measurable. The measure, the Lebesgue measure then of E, is defined as the infimum of the smallest optional sum of the Borel volume of all the capital I. So here we have the sum of the Borel volumes of all the capital I, and we can compute those volumes here with the measure we already defined. All right. So now let's go on with our example. So we want to integrate the Dirichlet function from 0 to 1. The Dirichlet function is defined like this. It has the value 1 for all rational numbers and the value 0 for all real numbers without the rational numbers. And it looks like this. So here we have the infinite but countable amount of rational numbers that have the value 1, and all the numbers that are the real numbers between 0 and 1 without the rational numbers have the value 0. Okay? The Lebesgue integral then is defined like this. So the measure of this volume here has the volume 1, and the measure of this volume has the value 0. But the measure of this volume, here we use the Lebesgue measure for it, and this one we can use the Borel measure for it. That's not a problem. So for this volume, the measure is just 1. This is Borel measurable, and no problem. So now we're going to look at the Lebesgue measure of A. So let's observe the interval from 0 to 1. All right? And then we can find a sequence for all those countable rational numbers here. Like this is the first, the second, third, and fourth rational number in the sequence that can reach all rational numbers in this interval, right? And then I find intervals which cover up all of them, right? Because we need to find the union like we did before. So for this interval, I chose 1 over 10, then I have 1 over 20 for the length of the interval of the second, a rational number, and 1 over 40 here for the third, and 1 over 80 for the fourth. So the union of those intervals make up our union of capital I that have to cover up A, right? And then the Lebesgue measure of A, Lebesgue measure of A, has to be smaller than the sum of the length of those capital I, right? In this case, this is just a geometric series, and it equals 1 over 5. So we know the Lebesgue measure of A is smaller than 1 over 5. But I could have chosen a smaller interval for the first, like 1 over 100. And then I would get an log that the Lebesgue measure of A has to be smaller than 1 over 50. I could also watch the limit, so I can make the first interval arbitrarily small, and then I will see that the Lebesgue measure of A has to be 0, because only then this here is true for all intervals that I can choose, right? And then I can see the Lebesgue integral is then 1 times 0 plus 1 times 0 times 1, which equals 0. So now the Lebesgue integral enables us to integrate this function.
Now the proof. We have to demonstrate that the properties of outer measures hold for the Lebesgue outer measure. There are 3 of them. Let mu be the measure. Then the measure of the empty set must be equal to 0. The second property is called monotonicity. Assume A is a subset of B. Then it has to follow that the measure of A is smaller or equal to the measure of B. The third and the last property, which is to show, is called sigma subadditivity. It says that if every set is a subset of omega, the measure of the countable union has to be smaller or equal to the sum of the images. We will start with the first property. The Lebesgue measure of the empty set is constructed by finding a union of Borel volumes that cover the empty set. However, the empty set is covered by the empty set itself, which is trivial. So the sum of the Borel measures of the covering intervals is just the Borel measure of the empty set, which is 0. Now the second property. To prove monotonicity, suppose that A is a subset of B. This is also very intuitive. If something covers up B, it also covers up A. Therefore, the second property is also true for the Lebesgue outer measure. The last property to show is sigma subadditivity. The Lebesgue measure is naively spoken the smallest possible sum of the Borel volumes of the covering intervals I. So if we add a positive value, we naturally get to the following equation. Notice that the intervals now have 2 indices. Because one is needed to cover up one certain ek, and the second one is due to the fact that we will observe a union of many ek. Because of monotonicity, it is easy to see that the sum of all sums of the Borel measurable intervals that cover up the corresponding volumes ek automatically covers up the union of the volumes E. The sum of the Borel measures is exchanged for the inequality we showed before. Now we split up the sum and realize that the second part of the sum can be written as a geometric series. Therefore, we have to lower the starting point of the sum to k equal to 0, which costs us this negative term here. Then we just compute the geometric series, which is possible because this term is smaller than 1, and we get 1 divided by n. So this inequality has to be true for any n. So we observe the limit n to infinity, which leads us to the result.